7 or 8 years ago, it wasn't really part of our vocabulary, but we knew about it. And part of it came from some of the work that we're doing in the city of Boston here. The mayor's office has an office which they call Office of New Urban Mechanics, which is very interesting because they're looking at smart ways to run cities better. And that was sort of the beginning of many collaborative projects that we started with it. And since then, of course, this has expanded, and now everybody is a smart city. Let me tell you first of all what my view of a smart city is. So, as you see here, we're looking at the city as kind of being a closed-loop system. And this is important because that's what the word smart contributes to. It's not just about data collection. Data collection is something that we can do now because we have a lot of sensors and sensor networks that are deployed throughout the city. And we have a lot of ways in which we can collect and process so-called big data. So we can convert the information that comes from the big data into useful information for making decisions, taking actions, and closing this loop, and then repeat this. So again, the intelligence, the smart part in smart city comes from the fact that we don't just collect data. Collecting data is half the story, and it's an absolutely essential part of the story, but really using the data to close the loop is what's important. And of course, in closing this loop, I don't want to oversimplify or underestimate the complexity of this process, so I have put here various concerns that we all have, such as the management of energy, safety, privacy, security, all have to be interconnected and being part of this whole big picture. Now, what I want to do is, in the limited time that I have, is give you just a potpourri of some of the projects that we're working on, which come under the heading of smart cities. So the first one is something we call smart parking. We actually developed an app that you can see here called BU Smart Parking. And this is a parking facility which is across the street from here, where some of us park every day, which we actually instrumented to turn into a smart parking system. I'll talk a little bit more about that, but this was perhaps one of the first smart city projects. Traffic light control. So the picture here is actually Commonwealth Avenue, and we are somewhere over here. And this is typically me every evening, like tonight, when I try to go home. And what I find is that I get stuck at every traffic light, the red light, instead of being able to drive straight through, even though at this time of day, typically between 7 and 8, there's hardly any traffic in all of these cross streets. There is a fair amount of traffic on Com Ave, but not much traffic in the cross streets. Why on earth can't we just turn the light green for the people who need it and needlessly keep it red? It's something that I'm sure everybody has wondered, and it's actually pretty easy to do. It's amazingly easy to do. All right, so more generally, when it comes to controlling the transportation system, this is a snapshot of the infamous 100-kilometer Chinese traffic jam entering day 9. Actually, it lasted 12 days, if I'm not mistaken. This is amazing. This should never happen. Okay? The fact is that we have a tremendous opportunity to alleviate a lot of these traffic problems with the emergence of what we call CAVs, connected autonomous vehicles, or if you prefer, connected automated vehicles. So essentially, it's an internet of cars that talk to each other, exchange information, and operate just so we can minimize the congestion levels, the energy that we consume, the emissions to the environment. It's a win-win-win-win-win situation if we do the job right. So I'll talk a little bit about this traffic control problem. I already mentioned about the Chinese congestion, but you don't have to go very far. If you go just down Com Ave and turn left, this is the BU Bridge. This is Com Ave. This is the BU Bridge. And this is the worst double intersection ever designed in the entire history of civilization. It is amazing. This is a simulation that we have run. We're on a mission to improve that. But basically, the problem starts from the fact that if you come from the BU Bridge, this is Cambridge, you're not allowed to make a left turn into Com Ave. I have talked to the city officials about why, and nobody knows why. Or there was a reason 15 years ago. So this starts a problem because all the traffic now has to come around this loop that you see here to turn right, including me every morning. Then, this little street over here is fed by traffic from here, and from here, and they want to go right, straight into Storrow Drive, across the VU Bridge, left into Comm Ave. This whole area over here fits maybe 7 or 8 cars. You can create deadlocks. And when you create a deadlock here, the traffic that's trying to come down from here gets stuck there. It's an incredible mess. We can do much better. So, if you wonder about why on earth is it that we cannot control traffic networks, there are really 2 main reasons that I can think of. The first one is the absence of controls. We just don't have enough controls. Okay? Things like traffic lights, yes, okay, but that's only in urban areas. And then speed fines and tolls are very indirect means. So there's no chance to use what we call feedback. And we know that feedback is the source of intelligence. The second reason is something that anybody who has ever done any work in game theory, elementary game theory, knows. When we play a game which is not cooperative, and we don't know what the other players are doing, yet we would we would like to achieve some kind of a cooperative objective, then bad things happen. As a result, all of us drive selfishly and we seek to solve our own personal problem, and that is far away from what we call the social optimum. The connected automated vehicles provide us an opportunity to move from this situation to this situation. I'm not going to show you the results, but Yanis and I, in fact, and some other people have done work with the actual traffic data of the Eastern Massachusetts Transportation Network in 2012, and we have shown, based on this data, that if you take the selfish traffic equilibrium that you can attain and switch into a mode in which you can tell everybody where to go and what to do, which is the automation of the vehicles, then you can improve and achieve a social optimum, which in many cases, depending on the time of day and time here, is 50 to 100% better. So it is amazing what we can accomplish. But we're actually trying to go a step further. We're trying to eliminate traffic lights and make our traffic, at least in intersections, really smart. I'll show you a little video to end my presentation where you can see how this would work. We have actually done that for the double intersection that I've shown you here. I don't have the videos to show you because it would take time to explain, but you will see that we can actually have all the cars move and never stop, and that's the holy grail. We are also doing, since we're talking about robotics, we're also doing a lot of work in the lab. So actually this is a little video where I want to show you how we project on the floor of our robotics lab that you will see when you visit EPIC, different urban landscapes. Here basically an intersection. And we use little cars here to play the role of little robots here to play the role of cars. And what you see here is red and green lights. In this particular movie, all we're trying to do is we're trying to make sure that the vehicles that you see here obey the rules. For example, here these guys are going to stop because the light is red, now it turned green, so you're going to go through. The first thing that we're trying to do is to control the red and the green light duration in a smart way to minimize congestion. The next step is to eliminate those and to have everybody go through without ever stopping. So this is one of the things that I wanted to show you because many of you here come from the robotics community, and we do need the robotic expertise to play games like that and to create what we call miniature city environments. Let me talk just a little bit about what I meant by smart parking. So by smart parking, what we mean is what I'll talk about in a second, but to motivate it, it is amazing if you look at the data to realize that 1 out of 3 cars in any big city in the world is actually looking for parking. And it takes about 8 minutes to find parking. So this is a real mess, and the current state of the system is that the drivers may not find a vacant space even if you tell them where it is. That's what nowadays is called smart parking. We'll tell you where there's parking, yeah, but you may not actually find it by the time you get there. You may miss a better space, and actually it's kind of hard to process information while you're driving. okay, because you have to keep on looking at your app. From the city standpoint also, you create a lot of imbalance, because different people go where they think they can find parking. And this is the worst. Not only do you not solve the parking problem, but you can make it worse. Because if I tell you on a nice little app that there's a parking space during a Red Sox game right here, then 100 people will converge there. One person will get it, and the other 99 will just keep on driving around, cursing at each other, and you actually make the matters worse. So this is not smart. Our idea of smart parking is basically this. You are here, you specify a destination in downtown Boston. This is where you really want to go, not where you want to park. And we will tell you what the best parking spot is for you, meaning closest to your destination and cheapest, in the sense that you could park on the street or you could park in an expensive garage, depending on what's available. And we will reserve it. So the reservation part is the tricky part, of course. I'm not going to get into the details of that. I do want to show you why this is an illustration of what we call smart. If you do not provide any guidance and a reservation scheme about where to go in terms of parking, essentially you're giving a vehicle, a driver, the information there's a parking space there, and then they're left on their own. Maybe they'll get it, maybe not. What is smart is to process this information and to close the loop, to actually not only guide the person to the best parking spot that we can find, but also reserve it for them. So that's what we do, and this is actually a little movie, the first incarnation of our smart parking system in the lab, so that's about 5 or 6 years old, where we implemented the reservation scheme using these barriers that you see here. When a vehicle is assigned to a particular parking space, then this is recognized, this is simple GPS technology, and the barrier opens just for you. Clearly you don't do that in the real world. In the real world what we do is we put at parking spaces little mini traffic lights. So a red means that this is reserved, you can't park there. A green means you can park, and a blinking yellow means this is your parking spot. And that's exactly what we have done in this implementation over here. You can't really quite see those little parking lights there, but that's what we have. And this is our smart parking app to do this. So I will close, taking any questions that you might have, but I'll show you what the world will look like, not too far off from where we are today. So just enjoy this little video. I will give you the sort of the caveat that this is not real, but it can be, except for the pedestrians. Oops, why isn't this showing? Sorry. I think I know why that is. I need to get out of my PowerPoint first, probably. Excuse me.
Did the cord come off?
No, it's it wants to stick to PowerPoint for some reason. So let me try to close my PowerPoint. Or we can try this. Yep. There we go.
Looks like today.
So this is an artist's rendition of a traffic lightless intersection. But as I said, we can do this, except for the pedestrians. Okay? We have ideas about how to do that. So if you ignore the pedestrians, everything else is very much doable. So that's it. Thank you very much.
So we can take 1 or 2 questions, and then we'll switch to the next speaker. Please.
Yes. So when you talk about cooperating vehicles, sending information to each other and getting and receiving commands. If a car is going to obey the commands that it's being given, then you need some certainty that it's getting commands from a good source, and that source is not defective. And since errors can occur, there's the question of how do you double check for that? Can the operator intervene or what? Moreover, it would seem, unless lots of care is taken, that someone who wants to hack the system can create quite a bit of havoc at any time. How are you addressing these issues?
Very good questions. The security one, I can't give you anything more than we're facing this every day with every problem nowadays with our cell phones, with our data, and so on. However,
life and death is more at stake than
absolutely,
cell phone.
yeah. There is a new protocol, if you will, which is for this Internet of Cars, called DSRC, which stands for, I forget, direct, or DSRC, I forget what it stands for. But it's think of it as a Bluetooth, a little enlarged for an area around an intersection. And that can be made more safe, secure. And there's a lot of people working on that. My second answer is robustness. Okay? There are ways in which you can compensate for errors like that. So a simple example is, obviously, we're not going to rely on just this network measuring the distance between two cars. We're going to have local sensors so that if something goes wrong and you get too close to the car, like pretty much you did today, you will stop. So you need a lot of loops to guarantee this, but the overall answer to your question is we don't know. It's the same ubiquitous problem of security that we face every day.
I would differ on that one, because life is at stake.
True. Yeah. But there are good answers to that. In fact, we can save a lot of lives that way, because a lot of the accidents that we see happen at intersections for silly reasons. So for every life that we lose because of the security threat, we can probably save about 50 or so. I don't have the statistics, don't quote me on that. But you're absolutely right. I'm not going to disagree, but there are many ways in which you can look at this.
There's a difference between giving warnings to the driver versus having the car operate based on commands which coming from external and seemingly unknown sources.
That's true, yeah. And there are different levels of this automation.
Question in the back?
Yeah.
Have you looked at any mixed driver-driverless scenarios that give you improvement over just driverless?
Yeah, in the literature, in the technology, there are 4 levels of automation, L1 through L4. L1 is what we have today, L4 is what I just showed you. What you're describing is referred to as L3. You provide guidance to people, but you keep the driver involved. It still doesn't solve the security problem, because by the time that I'm brought back as a driver into the loop, the damage may have been done by a hacker. But yes, and actually, the #1 question that I get when I give this talk is, there are 2 popular questions. Yours is actually #3, a security one. The #1 is, how do you mix next month the fact that there might be 2% of these fancy cars with the rest of the world which still drives the same old cars they had 20 years ago? How do you mix those? And there's an answer to that. It's possible to do it, but it's unknown right now what penetration level do we need to capitalize on the benefits of this automation. 2%, 3%, 50%, and these are economic factors that we have to take into account.
There's a question.
In a system where you have sort of collective, greater good from collective behavior, there might be incentive for people to cheat to do back to their self-optimizing behavior. So those systems where you can prevent that or incent them so their best behavior is in fact correct.
So if you keep the driver in the loop and therefore they can cheat, it's very easy to show that indeed you can cheat. There are different mechanisms that people have talked about, and some of us are working on that, to create incentives, or another concept which is called information nudging. It's not so much an incentive, it's nudging. It's just trying to get you to do the right thing, and you may not even know why you're doing it. But these are all very, very interesting topics, and they go beyond transportation, of course.